see the conformational analysis of cyclohexane. Cyclohexane is the most stable cycloalkane. Now when we talk about cyclohexane, see the term cyclohexane bears a part cyclo. It indicates it is a cyclic structure, and the term hexane, it indicates it is an alkane having 6 carbon atoms. So it is a cyclic alkane with 6 carbon atoms. This cyclohexane is considered as the most stable cycloalkane. It is strain-free, meaning neither angle strain nor torsional strains apply, and it shows the same stability just like chain alkanes. This spatial stability is because of a unique conformation which this cycloalkane, that is cyclohexane, adopts. What is that unique conformation? It is the chair conformation of cyclohexane. If the cyclohexane lie in a single plane, in that case it has got lots of angle strain as well as torsional strain. However, when it adopts the chair conformation, the angle strain or torsional strain is vanished. As a result, the structure becomes, or the conformation becomes, quite stable. The most stable conformation of cyclohexane is called chair conformation, since it resembles like a chair, or it resembles a chair. Now if we compare, or if we see these two structures, then this is representing a chair, whereas this is representing the conformation, chair conformation of cyclohexane. This part, which is lying down or facing down, it resembles this part, whereas this part which is facing up is resembling this part, whereas the remaining part, the parallel part, resembles to the sitting area. Now, in the chair conformation of cyclohexane, all the carbons are at 109.5 degree bond angles. So there occurs no angle strain. The hydrogens on adjacent carbons are also arranged in a perfect staggered conformation, which makes the ring free of torsional strain as well. Okay. Now here I am trying to explain why this chair conformation of cyclohexane is considered as most stable. Here the reasons are: in chair conformation, all the carbons, they lie at 109.5 degree bond angles. So there is no question of angle strain. The hydrogens on the adjacent carbons, here we can see, they are oriented in such a way that they lie in perfect staggered conformation, which makes the ring free of any torsional strain as well. So there is no angle strain, no torsional strain. When these atoms, they lie close to each other, they give rise to torsional strain. When they are in staggered orientation, they are maximum distance apart from each other, which represents staggered conformation, and in staggered conformation the torsional strain is minimum. This will be illustrated more clearly when we learn about the Newman projection of the chair conformation of cyclohexane. Now let us see the properties of the chair conformation. When we draw the chair conformation of cyclohexane, if we do not show the orientation of all the hydrogen atoms which are attached to all the 6 carbon atoms of cyclohexane, then the structure is not considered complete. In the chair conformation of cyclohexane, there are total 12 carbon hydrogen bonds, which can be divided into two categories based on their orientation. There are 6 axial bonds and 6 equatorial bonds. There are total 6 carbon atoms. Each carbon atom is associated with 2 hydrogen atoms. Of these 2 hydrogen atoms, one is axial and one is equatorial. If we observe, in all the carbons, we can see one axial hydrogen and one equatorial hydrogen. Now, when we sum up these hydrogen atoms, that is all the axial and all the equatorial hydrogens, we can say, or we can come to the conclusion that there are total 6 axial hydrogens and 6 equatorial hydrogen atoms. The axial bonds are vertical and perpendicular to the average plane of the ring, while the equatorial bonds are more flat and extend from the perimeter of the ring. Both the axial and the equatorial, that is A and E, they can either point up or they may point below the ring. Okay, they may point up or they may point down. Here we can see axial up, axial down, equatorial down, equatorial up. Now here observe one thing, the adjacent hydrogen atoms, or the hydrogen atoms which are attached to the adjacent carbon atoms, they are oriented in such a way that if the hydrogen atom which is attached to the first carbon, it is lying up, then the axial hydrogen on the adjacent carbon will be facing down. It will be pointing down. Likewise, the equatorial hydrogen attached to the first carbon, if at all it is pointing down, then the equatorial hydrogen at carbon number 2 will be pointing up. So this way we can observe that the axial and equatorial hydrogen atoms, they are alternatively lying up and down, down, up, down, up. Here, down, up, down, up, down, up. Okay, so this alternative up, down position is present alternatively along the cyclohexane ring. Each carbon has got one axial bond and one equatorial bond. If one bond points up, the other has to point down. Now here, see, if axial bond is pointing up, equatorial bond is pointing down. Likewise, here axial bond is pointing down, equatorial is pointing up. Similarly, we can see the same case, or we can observe the same thing repeated at all the carbon atoms. For the same type of bonds, the orientation up and down alternates from one carbon to the adjacent carbon. Meaning, if a certain carbon has axial up, then the adjacent carbon, here we can see, here the axial hydrogen is pointing up, whereas the adjacent carbon has got axial hydrogen pointing down. So in all we can say, for the total 12 carbon hydrogen bonds, we have got 3 axial upward directing bonds, whereas 3 axial downward pointing carbon hydrogen bonds, 3 axial upward carbon hydrogen bond, and 3 axial downward pointing bonds, carbon hydrogen bonds. Now, how to draw the chair conformation of cyclohexane? Now let us see. We will see it in a stepwise manner. First, we have to draw two parallel lines of the same length and both are pointing slightly down. If connected, they would have formed a parallelogram with an internal angle of 60 or 120 degree. Okay, in that way we have to draw the parallel lines. Okay, to start with, we can say we have to draw two parallel lines and they should be slightly inclined. They should not be parallel or they should not lie straight. They should be inclined. Now we have to connect the right ending points of the two lines with a V shape. Here we can observe the V shape so that the vertex of the V points to the upper right. Here we can see the vertex of the V, it is pointing to the upper right. In a similar way, we have to connect the left starting points of both the parallel lines using a V shape so that the vertex of the V points to the bottom left. Here we observe the vertex of the V points to the right top, whereas here the vertex of the V, it points towards the bottom left. Now we have to add up all the axial bonds on each of the carbon as all vertical lines. Axial bonds are shown with vertical lines. Here we can see alternative vertical lines. Here upward pointing vertical line, here a downward pointing vertical line. Similar situation is repeated at all the 6 carbon atoms. Now we have to add all the equatorial bonds by following the trend in which on a certain carbon, if an axial bond is pointing up, then the equatorial bond must point down and vice versa. Okay, so if here we can see, if this is pointing up, this should point down. Here it is pointing down, so the equatorial bond should point up. Now here we have to notice, we have to notice one more fact, that the equatorial bond is parallel to the carbon-carbon single bond, which is one bond away, as we can see below. Here we can see the green E line, the green E, equatorial carbon-hydrogen bond, is parallel to the carbon-carbon bond shown in green color, and the blue equatorial carbon-hydrogen bond lies parallel to the carbon-carbon bond shown in blue. Now when we draw a cyclohexane structure and we want to show the axial and the equatorial bonds, the presentation or drawing the equatorial bonds become more challenging as compared to draw the axial bonds. So if we follow this trend, then it becomes easier to draw the equatorial bonds as well. Now let us see what is ring flipping. When a cyclohexane ring undergoes chair-chair conformation conversion, the concept or the phenomenon is called as ring flipping. Now if we observe these two figures, here we can see the V at the left hand side is pointing down and the V at the right hand side is pointing up. When it undergoes ring flipping, what will happen? This V at the left will move up and the V at the right hand side will move down, and we get the flipped structure of cyclohexane. Ring flipping comes from carbon-carbon single bond rotation. However, since all of the bonds are limited within the ring, the rotation can occur only partially. And this partial rotation of bonds leads to the ring flipping. Cyclohexane rapidly interconverts between two stable chair conformation because of the ease of bond rotation. The energy barrier between these two structures is about 45 kilojoules per mole, and the thermal energy of the molecules at room temperature are great enough to cause about 1 million interconversions to occur per second. I repeat this point. The energy barrier is about 45 kilojoule per mole, and the thermal energy of the molecules at room temperature are great enough to cause about 1 million interconversion to occur per second. Here all the axial bonds become, after ring flipping I am talking about, all axial bonds become equatorial and all equatorial bonds become axial. Here we can observe when this ring flipping takes place, this V is flipped up and this V is flipped down. Ring flipping occurs resulting in the structure. Here we can see the axial bond here is pointing up here, and when the ring flip up, what will happen? Here we can see the equatorial hydrogen, which was shown like this, is supposed to move up. Okay, so equatorial bonds become axial and the axial bonds, which is shown in red color, it acquires axial position. Okay, here when we see this carbon-carbon bond between carbon number 1 and carbon number 2, we can compare the carbon number 1 and carbon number 2 with this orientation. This is the orientation prior to ring flipping and this is the orientation after ring flipping. Here we can see hydrogen at this carbon number 1, axial hydrogen, equatorial hydrogen, it becomes axial here, and the axial hydrogen here becomes the equatorial hydrogen here. Similarly, at carbon number 2, the axial hydrogen has become, it is replaced with the equatorial hydrogen with its blue color. The axial hydrogen has taken an equatorial position. So if we see the orientation of the carbon hydrogen bonds, we can observe that the axial bonds has converted to equatorial positions or bonds at equatorial position, and the bonds which were earlier lying at axial positions has now acquired axial position, sorry. Now let us see the Newman projection of the chair conformation. The chair conformation is a strain-free structure with all the carbon-hydrogen bonds in staggered position. However, it is not that easy to see the staggered conformation in the drawings we have so far. And Newman projection is going to help here for the shape. Here Newman projection will help for this purpose. Now to draw the Newman projection for the chair conformation of cyclohexane, we also need to pick up the carbon-carbon single bond from which or along which we want to view the structure. Just as we saw in case of earlier alkanes. Since there are total 6 carbon-carbon bonds, we will pick up only 2 of them. Here we have taken the carbon single bond between carbon number 1 and 2 and the carbon-carbon single bond between carbon number 5 and 4. These 2 parallel bonds are taken into consideration from which we want to observe the structure. Bonds, we will pick up only 2 of them, and these 2 need to be parallel to each other. Now our purpose is to draw the Newman projection of this chair conformation of cyclohexane. So first what we have to select, 2 parallel bonds, and we have to define from which angle we want to observe it. Now we have numbered this cyclohexane, all the carbon atoms, 1, 2, 3, 4, 5, 6. Okay. Now when we have fixed the axis of observation, now as we know, there are total 3 pairs of parallel bonds in the chair conformation. Any pair can be picked up in order to represent or in order to show the Newman projection. Okay. Here for the chair conformation, the 2 blue parallel carbon-carbon bonds picked here for viewing the structure of cyclohexane is C1, C2 and C4, C5, C4. Here we can see C5, C4, C1, C2. Once this is done, for the carbon 1 and 2, that is C1 and C2, C1 lies in the front, that is C2 lies at the back. Whereas here C5 lies in the front, whereas C4 lies in the back side, or it represents a rear carbon. These 2 bonds will be represented by 2 Newman projection, the carbon at one end, the carbon at second end, or the axis at second end, the observational site at the first end, second. There are 2 ends. Carbon lying at the front, here is the carbon number 1. Here it is shown with this. And the carbon at the rear is carbon at position number 2. It is shown using a circle. Here carbon at the front is 5, carbon number 5 is shown like this. Whereas carbon at the 4th position lies at the rear side. Hence it is shown using a circle. Next remains the axial and equatorial hydrogen atoms. Okay. As we have already discussed, they lie in perfectly staggered orientation. Hydrogen attached to carbon number 1. It is shown by this thing. And the hydrogen lying, the equatorial hydrogen is shown like this. The second hydrogen is shown like this. Likewise, the 2 hydrogens attached to second carbons are also shown in a similar manner. Similarly, the hydrogen atoms attached to carbon number 5 and 4 are also shown in staggered conformation. Now, with this, we have represented carbon 1, 2, carbon 4, 5. What about carbon number 3 and 6? If at all we want to represent the entire structure of cyclohexane using Newman projection. keep in mind that there are a total 6 carbon atoms in the ring, and to draw the above only so far as we have discussed till now, only 4 of them are shown, whereas C3 and C6 has been left behind. Now these two separate Newman projections are connected through the carbon number 3 and carbon number 6, and how they are connected, that we will see here. When we connect these two ends to this carbon 3 and carbon 6, then only we get the overall Newman projection of the chair conformation of cyclohexane. And how we are supposed to join them? If we see the earlier structure, carbon number 2 is attached to carbon number 3, and carbon number 5 is attached to carbon number 6. So carbon number 2 is attached to carbon number 3 directly. The ring is attached to CH2, and the carbon at position 5 is attached to carbon number 6. So in this way, we can exactly say where to place the carbon number 3 and where to place the carbon number 6. And once the position of carbon 3 and carbon number 6 is established, the perfect staggered conformation of all the carbon atoms, or the presentation Newman projection of the entire structure is quite clear. The staggered conformation of hydrogens are also shown very clearly in this Newman projection. The axial and equatorial bonds on the 4 carbons, that is carbon 1, carbon number 2, carbon number 4 and 5, are shown explicitly, while the bonds on carbon number 3 and 6 are just shown as CH2. The vertical red CH bonds are representing the axial bonds, whereas the flat and the blue carbon hydrogen bonds are representing the equatorial bonds. Now, if we see this line, this dashed line in the drawing can be regarded as the average plane of the ring. And those atoms which lie above this line are the bonds pointing up, whereas those which are lying below are considered as pointing down. This is the average plane. So this is representing as it is lying up, lying below, up, below. Okay, so using this Newman projection method, in this way we can represent the conformation of chair conformation of cyclohexane. Now let us see the next conformation. It is not like that cyclohexane has got only one conformation. It has got other conformations also. So let us see what are the other conformations of cyclohexane that are possible. The next possible conformation of cyclohexane is the boat-like conformation. The chair conformation is considered as the most stable one with the lowest energy, because it is most stable energy-wise. It is less energetic, but it is not with this with a chair conformation where this end is pointing up and this end is pointing down. Now when we move this thing up and this thing down, an intermediate orientation comes where both the V ends, they lie up and the structure resembles that of a boat. Hence we call this conformation as boat conformation of cyclohexane. Okay. Now when we observe the hydrogen atoms attached to this, attached to the 6 carbon atoms of this cyclohexane, we can observe that the hydrogen atoms which are attached to this top end of this V-like structure, these 2 hydrogens atoms, they tend to come very close to each other. As a result, there occurs some interaction, and this interaction, as because it is coming into purview because of this orientation or change, or it occurs due to this ring flipping, or during this ring flipping, this orientation is called, or this interaction is denoted as flagpole interaction. This is the position where the 2 adjacent hydrogen atoms are most closer. So there occurs some strain in the ring. The boat conformation comes from partial carbon-carbon bond rotation. Why partial rotation? Because when we move from chair conformation towards boat conformation, only one part, or only one V part which was lying earlier down, is moved up. The second side is not moved. So it is a partial ring flipping. Now, when flipping occurs, only flipping one carbon up to convert the chair to a boat conformation takes place. And of the chair conformation, only one part is flipped up, and all the carbons, all the remaining carbons, they still have got the same sp3 hybridization with bond angle 109.5 degree. So there is no question of angle strain in case of boat conformation. However, the hydrogens on the base of the boat are all in eclipsed position. As a result, there are torsional strains. Now, if we see all the hydrogens, they lie parallel to each other, and in such a way that they lie just parallelly back to back. As a result, we get eclipsed type of orientation, or we can say we get eclipsed orientation. Now, if we observe this structure across this bond bearing carbon number 5 and carbon number 6 from this angle, what we can see is this hydrogen, they lie just back to back. Likewise, this and this hydrogen, they lie back to back. Likewise, these 2 lie back to back, these 2 lie back to back. So they represent perfect eclipsed conformation. When there is eclipsing, that leads to torsional strain, because the atoms, they try to interact with each other when they come far closer to each other. Now, when we try to represent this boat conformation of cyclohexane using Newman projection, this projection will look like this. Carbon number 5 and 6 is taken as the axis of observation, keeping carbon number 6 at the front and carbon number 5 representing the rear side. So observation is done from this side. If at all we observe the same molecule across the parallelly placed carbon-carbon bond, it is C2C3 bond, or the bond between carbon number 2 and 3, the site of observation or the angle of observation being this one, you can see carbon number 2 or carbon at position number 2 lies at the front and carbon at the position number 3 lies at the back. So 3 represented using a circle, 2 is represented using an intersection of lines. Position of all the hydrogen atoms are shown in their eclipsed orientation in this way, whereas carbon number 1 and 4 are attached to carbon number 6 at carbon number, you can see it is attached to carbon number 3. So carbon number 6, carbon number 1 attached, carbon number 4 is attached to carbon number 6, whereas carbon number 1 is attached to, carbon number 4 is attached to carbon number 5 and carbon number 1 is attached to carbon number 6. And this way we can see the entire boat conformation of cyclohexane, which is having lots of strain, torsional strain. The two types of strains which make this boat conformation to have considerably high energy is than that of chair conformation is the flat pole interaction and this eclipsing of all the hydrogen atoms, and they lead to an energy difference of 30 kilojoule per mole as compared to the boat conformation, chair conformation of cyclohexane. Apart from boat and chair conformation, we can also see some other conformations possible with cyclohexane. The next possible conformation is twist boat conformation. And here we can see the boat conformation, which is twisted somewhat to get a conformation like this. And here, if we observe, here the flagpole interaction was high because these two hydrogens are quite closer to each other. Now, when we talk about this twist boat conformation, these hydrogen atoms, they move away. As a result, the flagpole interaction is reduced. Okay, twisting of the boat results in the release of steric strain due to flagpole interaction. The next possible conformation of cyclohexane is half chair conformation, where one of the elevated side or V-like part of this boat conformation is made coplanar with this plane of the ring. As a result, the structure becomes somewhat like this. If the carbon number 1 or carbon number 4 of the chair conformation is brought in average plane of the ring, then the resulting conformation is known as the half chair conformation. Now, if we compare the stability of all these 4 conformations it has, or we can come to the conclusion that the stability of chair conformation is maximum, whereas the stability of half chair conformation is minimum. Now, if we compare these two, then twist boat has got higher stability as compared to boat conformation. And when we compare the stability of all the four, the chair conformation has got highest stability as compared to all the three. Twist boat has got better stability as compared to, or more stability as compared to boat and half chair conformation. However, it is lesser stable as compared to chair conformation. Likewise, this boat conformation has got higher stability as compared to half chair conformation. However, its stability as compared to these two conformation is lesser. So we can say chair conformation is most stable, whereas half chair conformation of cyclohexane is least stable. Now, if we plot the conformation of all these conformations of cyclohexane and their energy contents, then we can observe that the chair conformation is having minimum amount of energy and maximum amount of stability. Now, when this part is flipped up, we get half chair conformation. We are flipping it partially up so that it comes parallel to this side, and we get half chair conformation, and its energy is very high. However, when this side is further flipped, we get boat conformation. However, in between these two conformation, we get the twist boat conformation, which is having lesser energy. And when we move to the boat conformation, the energy of the conformation increases and the stability decreases. Next, when from this boat conformation, we move towards this flipped chair conformation, again we will move through a twist boat conformation followed by half chair conformation, and then only we will move to this, or we can reach to this flipped chair conformation. Now, if we observe the energy difference, we can see the half chair conformation is showing maximum energy. As a result, these half chair conformations are representing less stable structure or least stable conformation of cyclohexane. Now, if we compare the boat and twist boat conformation, we can see the boat conformation has got higher energy as compared to the two twist boat conformations. The energy gap between these boat and twist boat conformation is shown here. Next, when we move from half chair conformation to chair conformation, the energy gap, here we can see 12 kilocalories per mole and 50.6 kilojoule per mole. This is these two terms, they are differing only in terms of the unit of measurement. Here, either you can express it as 12.1 kilocalories per mole, or else you write only 50.6 kilojoule per mole, whichever you feel comfortable. If you want to express the energy difference in both the units, you are most welcome. So this way, we can compare the energy content of all the orientation to be specific, all the four conformations of cyclohexane. Now, if we compare the conformational interconversions of cyclohexane, we can come to the following conclusions. At room temperature, there is a rapid interconversion between two chair conformation, which we have already discussed. Almost about 10 million interconversions they used to take place. The interconversions start at one side of the chair to produce a twist-boat conformation. Then the other side flips up to form the boat form. Then the earlier side then flips again to form the chair form, and then the interconversions, then all the interconversions are opted like chair, half chair, twist boat, boat, twist boat, chair, and flipped chair conformation. These interconversions they require 49 kilojoule per mole of energy. The highest energy is associated with the half chair conformation. Here we can see the highest energy is associated with the half chair conformation, making this half chair conformation least stable. So with this, we come to an end for the